Good morning, children. This is lecture 2 of chapter Surface Chemistry. This lecture is based on catalysis. You are familiar with this topic. We have done a detailed study about the topic catalysis. This is just a revision. So, if you are facing any problem of understanding, please open the video for catalysis in chapter Chemical Kinetics. Catalyst and catalysis. The substances that alter the rate of a reaction but itself remains chemically unchanged at the end of the reaction is called a catalyst. The above process is called catalysis. Types of catalysis. Depending upon the phase of the reactants involved, the catalysis may be categorized as homogeneous catalysis and heterogeneous catalysis. Now, homogeneous catalysis. When the reactants and the catalyst are in the same phase and the reaction system is homogeneous throughout, the catalysis is termed as homogeneous catalysis. That means if the reactants are in solid state, the catalyst also in the solid state. If the reactants are in liquid phases, then the catalyst also will be in the liquid phases. If it is so, then it is known as homogeneous catalysis. For example, oxidation of SO2 into SO3 by oxygen in presence of NO. Now, the SO2 is reacting with O2. Both are in the gaseous state, you can see here. And NO is acting here as a catalyst, which is also in the gaseous state. So, the reactants are also in the gaseous state as well as the catalyst is also in the gaseous state. So, it is an example of homogeneous catalysis, which is giving SO3. Now, hydrolysis of an ester in presence of mineral acids. Ester and water both are in the liquid phase. H2SO4 is the mineral acid acting as a catalyst, that is also in the liquid phase. So, it is an example of homogeneous catalysis. It is giving you acid and alcohol. Now, hydrolysis of cane sugar in presence of mineral acids. The same way, cane sugar solution, that means it is a liquid. H2O is a liquid phase and mineral acid also in the liquid phase. So, it is also an example of homogeneous catalysis, which is giving fructose and glucose. Now, transition metal compounds participate in homogeneous catalysis as they have the ability to change their oxidation state. Now, let us see the reaction. The reaction between iron 3 and vanadium 3, and this reaction is catalyzed by Cu2+. What is happening here? In the first step, this Cu2+ is reacting with one of the reactant, that is V3+, and it is giving Cu+. That means the oxidation state is changing from +2 to +1. And we are getting V4+. Now in the second step, this Cu+ is reacting with another reactant, that is Fe3+. And it is giving Fe2+. And again this Cu+ is changing to Cu2+. Okay. So that means at the end we are getting Cu2+, which is acting as a catalyst, unreacted. So what is the overall reaction? Fe3+, V3+, and we are getting Fe2+, V4+, and Cu2+ will come out as it is. It is not taking part in the reaction. Heterogeneous catalysis. when the reactants and the catalyst are in the different phases. The catalysis is known as heterogeneous catalysis. Example, combination of N2 and H2. You can understand that both are in the gaseous phase. In the presence of finely divided iron, that is the Haber's process, we are using that. Now see, N2 and H2 both are in the gaseous phase and iron is in the solid phase. We are getting NH3 by Haber's process. Combination of SO2 and O2. Both the reactants are in the gaseous phase. In presence of platinum metal or vanadium pentoxide, that is a contact process. So SO2 is in the gaseous phase, O2 is in the gaseous phase, and platinum and V2O5 both are in the solid phase. We are getting SO3. Now oxidation of NH3 by O2, that means both are in the gaseous phase again, and this is happening in presence of platinum gauge, that is Oswald process. The platinum is in the solid phase. That means the reactants and the catalyst both are in the different phases. So that is known as heterogeneous catalysis. The example of heterogeneous catalysis is the hydrogenation of ethene to ethane using nickel as catalyst. The reaction is given here. First of all, ethene with a double bond, nickel is reacting with ethene and it is loosely bonded with ethene. Now after that, hydrogenation, when the hydrogen is reacting with that, then nickel is now attached loosely with one carbon atom, and then with the second hydrogenation, nickel is coming out. It is not taking part in the reaction, it is acting as a catalyst here, and we are getting ethane. That means here ethene and ethane both are in the gaseous state and the nickel is acting as a catalyst which is in the solid state. So it is an example of heterogeneous catalysis. Next is types of catalysis. Depending upon the nature of catalyst, whether it increases or decreases the rate of reaction, it may be classified as positive catalyst and negative catalyst. The catalyst which increases the rate of the reaction is called positive catalyst, and the phenomenon is known as positive catalysis. And the catalyst which decreases the rate of the reaction is called a negative catalyst, and the phenomenon is known as negative catalysis. Now some examples of positive catalysis. Decomposition of KClO3 takes place rapidly and at a lower temperature when a small amount of MnO2 is added to it. So MnO2 here is acting as a catalyst. Because of the presence of MnO2, the decomposition of KClO3 takes place rapidly and at a lower temperature. So this is an example of positive catalysis. KClO3 on decomposition giving you KCl plus 3O2. Decomposition of hydrogen peroxide takes place rapidly in the presence of colloidal sulfur. This is also an example of positive catalysis. Oxidation of hydrochloric acid into chlorine is accelerated by the use of CuCl2. So these all are the example of positive catalysis. Now some examples of positive catalysis. Decomposition of KClO3 takes place rapidly at lower temperature when a small amount of MnO2 is added to it. So you all know about it. KClO3, when it is decomposing, it is giving you O2 but MnO2, should be present as catalyst. Decomposition of hydrogen peroxide takes place rapidly in the presence of colloidal sulfur. So the sulfur is acted as catalyst. Now oxidation of hydrochloric acid into chlorine is accelerated by the use of CuCl2. So these all are acting here as catalyst, and they are positive catalysts. They are increasing the rate of the reaction. So they are known as positive catalyst. Examples of negative catalysis. Oxidation of sodium sulfite by air is retarded by the presence of alcohol. That means alcohol is acting here as a negative catalyst. Decomposition of hydrogen peroxide decreases in the presence of acetanilide. Oxidation of chloroform in the presence of air is retarded in the presence of alcohol. Tetraethyl lead, which is known as TEL, decreases the knocking of petrol and thus acts as a negative catalyst. That means tetraethyl lead is also acting as a negative catalyst. So these are the examples of negative catalyst. Some different types of catalysis depending upon whether the catalyst is a reactant or a product. The catalysis may be defined as autocatalysis, and the second one is induced catalysis. Autocatalysis. When one of the product formed itself acts as a catalyst, it is called autocatalyst and the process is called autocatalysis. Now see the example. The oxidation of oxalic acid by acidified potassium permanganate is represented by the equation MnO4 minus C2O4 minus and 16H plus is giving you Mn2 plus CO2 and H2O. Now this Mn2 plus, which is formed as the product, because of the presence of this Mn2 plus, this reaction gets accelerated after some time. Okay, that means this Mn2 plus, which is formed as a product, acting as a autocatalyst here, and because of that the reaction gets accelerated and the process is known as autocatalysis. Induced catalysis. When a reactant accelerates another reaction which may not otherwise take place under the same conditions. Again I am repeating, when a reactant accelerates another reaction which may not otherwise take place under the same condition is called induced catalyst and the process as induced catalysis. See the example. Sodium arsenide is not oxidized by air. Sodium arsenide is not oxidized by air, but if air is passed through a mixture of sodium arsenide and sodium sulfite. There's a mixture of sodium arsenide and sodium sulfite. If air is passed through this mixture, then both of them undergo simultaneous oxidation. Okay. Sodium arsenide alone is not oxidized by air. But when air is passed through a mixture of sodium arsenide and sodium sulfite, then both of them undergo simultaneous oxidation. Here, oxidation of sodium sulfite induce the oxidation of sodium arsenide. I think it is clear to you. Theory of catalysis. Number one, that is intermediate compound theory of catalysis. And the second one, adsorption theory of catalysis. Intermediate compound theory of catalysis. According to this theory, the catalyst react with one of the reactants first to give an intermediate. Now that intermediate will react with another reactant to yield the product, and the catalyst will come out as it is because the catalyst is not taking part in the chemical reaction. So how it is happening? What is happening? Suppose there is a reaction going on between A and B. Now first, the catalyst is reacting with A, one of the reactant, and it is giving you an intermediate. Now that intermediate is now reacting with B and it is giving you the product, and the catalyst will come out as it is. Just see this example. SO2 when reacting with O2 in presence of NO as catalyst, it is producing SO3. First of all, in the first step, what is happening? This catalyst NO is reacting with O2 and it is giving you NO2. Now this NO2 is reacting with another reactant, that is SO2, to give SO3, and NO is come out as catalyst. So this theory suggests that a catalyst provides an alternative path of lower activation energy by forming an intermediate compound with one of the reactants. This is known as intermediate compound theory of catalysis. The next is the adsorption theory of catalyst. Adsorption theory has been proposed to explain the mechanism of heterogeneous catalytic reaction, contact catalysis, particularly involving two gaseous substances over a solid surface. The heterogeneous catalysis, that is a gaseous reaction on a solid surface, may be explained by the theory how A gas, B gas, and the catalyst is in the solid phase, and we are getting C and D, both are also gas. So that means the reactants and the catalyst, both of them are in the different phases, different states. So that is known as heterogeneous catalytic reaction. Following four steps are involved in the heterogeneous catalysis. The first is diffusion of reactants at the surface of the catalyst. Catalyst is a solid. Now the reactants are diffusing at the surface of the catalyst first. Then the adsorption of the reactants at the surface. So catalytic surface is adsorbing the reactants. Adsorbing means it is a surface phenomenon. The reactants are not going inside. It is whatever happening at the surface only. Then third is a reaction of the reactants at the surface. As I told you, the reaction is happening at the surface only. Surface of the catalyst. Then desorption of products from the surface. Then again the products are coming out from the surface, leaving behind the catalyst as it is, because the catalysts are not taking part in the chemical reaction. Look at the figure. The figure below demonstrates various steps in heterogeneous catalysis. See here, there are two reactants shown in green and yellow color. And this is the surface of the catalyst. Now in the first step, the green molecules are coming and sitting at the surface of the catalyst, or they are landing on the active sides of the catalyst. And the second step, the yellow molecules are also coming and sitting with the green molecules, maybe in a proper orientation, so that the more collisions can occur, and because of the collisions, it will give the product. These are the product. So they are coming out from the surface of the catalyst and leaving the catalyst unreactive. They are not taking part in the chemical reaction. Now let us see what is written here. Step 1. Incoming species land on an active site and forms bond with the catalyst. It may use some of the bonding electrons in the molecules, thus weakening them and making a subsequent reaction easier. Step 2 and 3. Adsorbed gases may be held on the surface in just the right orientation for a reaction to occur. I have already told you. The adsorbed gases means these are the reactants. They may held on the surface of the catalyst in just the right orientation maybe, and that is why the reaction is taking place. This increases the chances of favorable collision taking place. There is a rearrangement of electrons and the products are then released from the active sites. I hope you have understood. General characteristics of solid catalyst. Number 1, the catalyst remain unchanged in mass and chemical composition in the reaction. Number 2, a small quantity of the catalyst is required. That you all know, that a very small quantity of the catalyst is required. Next, the reactants must get adsorbed into the catalyst strongly, but not too strong to become immobilized. Next point, the catalyst does not change the equilibrium constant. It is not changing any equilibrium constant, but the equilibrium approaches earlier. Next point, a catalyst exhibits maximum activity at a particular temperature, which is known as optimum temperature. Next point, the activity of a catalyst is depending upon the surface area. So the surface area of a catalyst is important in governing the activity of the catalyst. That is why fine divided metals are preferred as catalysts. Next point is, catalysts are selective in context of a particular chemical reaction. It is different for different reaction. For the same set of reactants, change in catalysts leads to change in product. Just see here the example. In all the three cases, the reactants are CO and H2. In the first case, nickel is the catalyst. We are getting methane. In the second case, copper is the catalyst. We are getting aldehyde. And in the third case, copper, ZNO and Cr2O3, the product is acid. Okay. Next, catalyst may be specific for a specific reaction. That you all know. For example, uricase only act on uric acid, while arginase act on arginine. Next point, a catalyst cannot make impossible reactions to occur, and it does not initiate a reaction. Next, certain substances decrease or destroy the activity of catalyst. Such substances are known as catalyst poisons. For example, arsenic destroys the catalytic activity of platinum in the manufacture of sulfuric acid. If we'll give arsenic with platinum, which is acting as a catalyst in the manufacture of sulfuric acid, with that, if we'll add little bit of arsenic that destroy the property of catalytic property of platinum, and then that arsenic is known as catalyst poison. Next is, some substances increase the activity of the catalyst, just opposite of the previous one. Such substances are known as catalyst promoters. You are familiar with that, promoters, this word. For example, molybdenum acts as a promoter in the manufacture of ammonia by Haber's process. In the Haber's process for the manufacture of ammonia, you know that nitrogen and hydrogen reacting together, where iron is act as a catalyst and molybdenum is act as a promoter, which enhance the activity of the catalyst. Shape selective catalysis. When catalytic reaction depends upon the porous structure of the catalyst and sizes of reactant and product molecules, the reaction is known as shape selective catalysis. For example, zeolites have honeycomb structure, which is very efficient in converting alcohols into gasoline. Am I clear to you? This is known as shape selective catalysis. Effect of catalyst on the rate of reaction. The function of a catalyst is to lower the activation energy of the reaction. In the presence of a catalyst, the reaction follows a path of lower activation energy. Catalyst is doing that work. Without the catalyst, the activation energy is more. And because of that, the reactant molecules has to cross that barrier, that activation barrier. And if we will add a catalyst, then it is lowering the activation energy so that more reactant can react. More reactant can cross that activation energy. Because the activation energy is getting lowered with the help of a catalyst. Under this condition, a large number of reacting molecules are able to cross over the energy barrier, whatever just I said, and thus the rate of the reaction increases. Just see the figure. This figure is showing, the first figure is showing the reaction without a catalyst. Now this is the activation barrier. So the reacting molecules has to cross this energy barrier. Okay. Now when a catalyst is used, it is decreasing the activation energy. It is lowering the activation energy and giving a different path. This dotted line is for the path without catalyst, and green one is showing the path for the reaction with the catalyst. And you can see that the activation energy is decreasing when we are using the catalyst. So more and more number of reacting molecules are able to cross this energy barrier. So it is increasing the rate of a reaction. Okay. Now this is the end of lecture 2. And next class we shall study colloidal state.